Hey, what's up, dude?
I'm good. How are you?
I'm doing all right.
Okay, nice. Nice to see you.
Nice to see you too.
Wait, let me give you
Access.
studying opportunity, yeah? How do I do that?
Is this being recorded or no?
I don't think it will be recorded, but if you want, you can.
No, I think I made a practice recording. I'll probably put that one up, but it'll depend what I say.
Yeah. I'm tired. You just.
I'm tired too. I was just like making my slides like.
I see.
Yeah.
Uh-huh.
I've tried to give this talk like so many times, and I mean it's just like so hard to finish. Oh, let me close my OBS.
So you have an hour. I didn't tell you that, but you have an hour if you want.
Okay.
And then we have the questions later. So you have a little bit more time.
Okay. I probably was going to take an hour anyway. No. Oh, stop recording. Let's see. Stop. Sorry, no, not. Okay, so this video is a joint work with Anton Halato. It's a practice talk for my talk at in Leiden. That's going to be on Mochizuki's inequalities. So this I've given many different versions of this talk, and you can never finish. And right. So there's got a lot of videos on my YouTube channel that describe some of these things. So if you have never seen Spiro's inequality before, I would go watch that video, for example. Okay, so let's talk about Mochizuki's inequalities. So first, let's get this out of the way that I don't claim to understand Mochizuki's proof. I don't see it as complete and correct because there's a point of contact that I can't see. And that's all I really want to say about that. So just full disclosure. Okay, so the natural place to start with Mochizuki's inequality is Mochizuki's inequality. Okay, so in particular, we want to talk about corollary 3.12 of theorem 3.11 in IUT 3, the third of Mochizuki's papers. And then I kind of want to break down a bunch of words that are going to appear. Okay, so here is Mochizuki's inequality. Here's this corollary, and then what I've circled right there is Mochizuki's inequality. Okay, so okay, so what do I want to say about this? Oh, okay. So there's a bunch of different words that appear in this business. So there's a thing called a theta pilot object. There's the multi-radial representation of the theta pilot object. So from the theta pilot, you can make a region, and then you kind of like close you take the orbit of that region, and you close it up using these things called hulls, right? So there's these monoanalytic log volumes. I'll say a little bit about log volumes. And then there are the Q parameters, which are kind of associated to tape parameters and encode the minimal discriminants of elliptic curves. And you know, there's this weird constant C naught if you were to go look it up. So some of the things are important in the theory, and some of the things are not important in the theory. And this is the typical example of something that's not important, right? So you can just reformulate the entire thing as follows, okay? So that one inequality is so you know, you can have, yeah, that's all I want to say about this, is that you can reformulate it in terms of an inequality like so, right? So yeah. Okay, and so, but my point is that this is one that you don't want to think about, and I want to tell you kind of the things that you should think about and the things that you shouldn't think about when trying to parse all of this stuff. So I guess that's like one of the main difficulties of the papers is that you kind of run out of RAM in your head in order to store all the information. Okay, so there's lots of words, and you need to kind of somehow figure out a way to hold all the definitions in your head at one time. And a lot of the work that we did was to kind of boil a lot of this thing down to a lot more simpler language. Okay, so again, here's the inequality, and you don't really know what log of any of these things mean. And so this is what we're going to start to break this down. And I'm going to state this in a more familiar, maybe notation. Okay, so here's the inequality. Okay, so here is something that's equivalent to the corollary 3.12. Okay, so let's take an elliptic curve in initial theta data, right, which is this 7 tuple of things. And a lot of the talk is going to be really explaining the hypotheses that go into this theorem, right? Then we're going to have an inequality of two real numbers. Okay, the left-hand side is essentially the negative of the left-hand side of the Spiro inequality, which is kind of weird, right? But it turns out that the right-hand side is also going to be related to the minimal discriminant of an elliptic curve, the log of the norm of the minimal discriminant of an elliptic curve. And then you have to like divide by degree and then divide by 2L, where L is an auxiliary prime appearing in this initial theta data tuple. Okay, the right-hand side is a little weirder. Okay, so the right-hand side is a kind of an RK-Love divisor or a tuple of RK-Love divisors associated to a region. Okay, so there's going to be an exchange in this whole theory. There's an exchange between divisors and regions, just like you have in usual number theory, right? So you can encode an RK-Love divisor in terms of a subgroup of the Adeles and take the measure of that, or the log of the measure, or you can encode or you can encode the, or given a subgroup, you can make a divisor by taking the value, the measures of each of the pieces and putting it together. Okay, so this is in particular, so we're going to do something like that, but there's going to be a tuple of divisors, and there's going to be a region. Okay, and okay, so what is the, okay, so one thing that I didn't say is I didn't say what the why are we dealing with tuples. So we're dealing with tuples. This is an artifact of an anabelian geometry construction. So maybe you guys have heard of the theta, the tall theta function. And so there's a procedure for reconstructing the Tate parameters of an elliptic curve. And when you do that, so what you're doing is you're evaluating the Jacobi theta function at certain special values. You cannot reconstruct the values on the special points, sorry, on the nose. And so you're carrying around kind of a tuple of information, and that's the best you can reconstruct. So one of the ideas is, okay, so there's an interchange between divisors and regions. But one of the things that you do is you kind of like take the region associated to this thing that you evaluated, and what you do is you mess it up in kind of a maximal way. You take an orbit under group and monoid actions, or something that's not even that, which is this thing called the log link indeterminacy, and you make it so that this object that you construct is invariant under automorphisms of, say, fundamental groups and absolute Galois groups and all these things that you constructed it from. Okay, and the purpose later is to make some sort of substitutions, and that is supposed to give you, that's allegedly supposed to give you the relationship between the two degrees in the inequality. Okay, in order to make that comparison, after you mess up the region, you have to kind of unmess it up so that it can be encoded back into an RKLF divisor, and that's what this whole construction is. Okay, so all right, so like I said, here is actually the definition of U theta, and okay, so this is this region here. Okay, so all right, so this is the messed up version of the thing. So this is messed up via the indeterminacies, and if I have time, I'll try and talk a little bit about in2. All right. Okay, so back to our inequality. So the other big part about computing with this thing is, okay, other than being able to write down formulas for the bottom part, which is non-trivial, right, is to understand what your hypotheses are and what you're allowed to put into this inequality. Okay. All right, so let's talk about this. This is what's called initial theta data, and it's the definition of it is 3 pages long. It appears in IUT 1, section 3, and there's, you know, Mochizuki's writing has a style that is not, again, you run out of RAM when you start to think about these things, and so let me kind of just highlight some of the things. So there's a lot of auxiliary constructions, and then there's a big barrier to entry, right? So you have to be, you know, so for example, it uses his Ital theta papers, and there's, you know, some properties from anabelian geometry. There's stacks. There are, you know, it's got a lot of stuff going on. And so one of the things that I wanted to do was to simplify this, and so to see if you could actually put this into a computer, okay, or produce tuples of initial theta data in an automated way. And okay, so here's the tuple, right? It's this 7 tuple, and you'll notice, I guess, one of the things that I will remove is I'll simplify these statements, but this is a curve, and this is this is a stack, but later I'm going to replace that with a subgroup of L torsion of an elliptic curve. Okay. All right. So just to kind of show you that this is non-trivial, you know, there's a math overflow post where people are saying, you know, they discuss this, and it's still not solved. And they were saying that it would be interesting if we could have an explicit way of producing these things. Okay. And, you know, this is me pointing to it not being solved. And so also what did I want to say? Okay, so one of the things they realize is that you're not allowed to be CM. They have some discussion of semi-stability, not semi-stability, and things like this. Okay, so the reason that you're not allowed CM is because you need to not be of potentially good reduction, right? So all elliptic curves or CM elliptic curves are potentially good. I mean, that's one of the reasons. The other reason is that you want your Galois representation to be surjective, and those two things are related by the Naranov-Shafarevich criteria of Sayre Tate. It's kind of a mouthful to say that because Sayre and Tate proved it. Well, I guess for elliptic curves, I guess Naranov and Shafarevich did this. Okay, so anyway, they're still talking about CM here. Okay, let's get back to our tuple. Okay, so what is this initial theta data? Okay, so this is an elliptic curve over a number field. So the F is a number field in the first place as well. Okay, glad that one's easy. So this is an auxiliary prime. That's also relatively easy to describe. There will be some conditions on it related to the primes of bad reduction, the degree of the field, etc. Right? Okay, so using these two pieces of data, we can construct two auxiliary fields that we'll need for the purpose of defining other things. So I've tried to make this as minimal as possible. One is the L torsion field. And the L torsion field really knows all about the arithmetic of the elliptic curve and yeah, that's all I want to say is that a lot of the information, all of it goes through field theory, or can go through field theory. And then the other one is this field which I'll denote F naught, which is the field of moduli for the elliptic curve, which is Q adjoining the J invariant of the elliptic curve. Okay. All right. So, okay. So where it starts to get weird is, okay. So the V-bad mod, maybe I should have described that one first, but that is a collection of places of bad multiplicative reduction, and they're places of the field of moduli. Okay. So this is over a model of the curve over the field of moduli. Okay. So okay. So one of the things that you fix is from the field of moduli. So you usually think about that as Q. You can you get a lift to the L torsion field. So for every place, you're going to have a lift, and so the places in the bottom I'll call V typically. The lifted places that section will be called V underline. And so the purpose of that is to kind of Frankenstein some constructions that don't exist that Mochizuki believed was the key to solving some of his problems. So okay, so I said this is a non-empty set of bad places. That also rules out CM. I guess there's bad places over F0, but there's also conditions on the type of bad places. In particular, it excludes 2, for example, the prime 2. But I think that Mochizuki, and even Fisenko, Arata Minamita, and Veronica, and Yushiro Hoshi are doing some things there. Oh, here's my, okay. So I wanted to talk about this Frankensteining business and what this is all about. So why are we lifting places? What's going on? Okay, so this is so the M underline and the V underline are friends. This is the thing that was originally encoded in the stack that we have simplified, and so. Mochizuki's been obsessed with the construction of a global multiplicative subspace for some time. It's been 20 years since this paper. And so his original paper, this Hodge-Arkelov theory paper, had a problem with the estimates derived in there, these things called Gaussian poles, where if you took degrees of the line bundles, you would hope to get some inequality, and because you allowed poles, because these poles occurred, this made an issue. Okay, allegedly, that this is the realization of this idea of removing the poles from the computation in the original Hodge-Arkelov papers. Okay, so this is the motivation for what he's doing. All right, so okay, so I think that I am going to talk a little bit about what this global multiplicative subspace is. Okay. So, but first we need to recall that if you have an elliptic curve with multiplicative reduction, right, over a p-adic field, that you have this Tate uniformization. Okay, you have a Tate curve which is algebraic, and the Tate uniformization which is a rigid analytic thing like this, and then a map between them. So you can in the coefficients of the Tate curve are written in terms of the Tate parameter. Okay, and when you have this situation, right, there is a so-called canonical splitting, right, where you can, I guess this top one should be Q, the Tate parameter 1 over L adjoin this thing. Anyway, there's always the L torsion in this model here looks like lth roots and torsion, lth roots of the Tate parameter and torsion in a root of unity. And so the Galois group acts by the cyclotomic character on this piece, right, on the root of unity piece. And sometimes we have a special notation for when a module acts by the cyclotomic character, and that's this little one thing. Okay, and then here you have a trivial Galois action. Okay, and so there's this splitting of the Tate module into these things, and this deals with this theory of transactions, which is, say, in like Silverman, the later chapters of the advanced topics. Okay, so what about this canonical splitting? So the global multiplicative, so I guess the roots of unity part is the multiplicative subspace, the local multiplicative subspace. Okay, and so what we want is some. So for the global multiplicative something, we want something that specializes to this at decomposition groups. Okay, so what we want is we want a subgroup of L torsion, right? So like a subspace. So this is isomorphic to Z mod L squared, so FL squared. And so we want some subspace, one-dimensional subspace. Okay, and to describe the condition that I want, I need to introduce two things. One is the mod L Galois representation. Okay, so that just acts on the torsion. And it also factors, so sometimes I write the K bar, sometimes I don't write the K bar, but it factors through K. Okay, so that Galois group is this representation factors through K. Okay, in this group we have these decomposition groups. Okay, and so what we can do is we can look at how these decomposition groups act on M, right? And what we want is we want those decomposition groups, when they act on M, we want M to be the torsion part. Okay, so these torsion points could just as easily be viewed in those p-adic fields, and so it makes sense to talk about these groups after you define these embeddings to these groups acting on that space. Okay, so yeah, these are decomposition groups at bad multiple places. And now we're kind of like talking about E is a global thing, and now we're talking about what happens when we specialize this construction. So what do we want to happen, right? So we want that when this thing acts on M, it'll be so when we kind of do this restriction, that this acts as this multiplicative group, or this it'll have this root of unity representation. Okay, so the point is that this is impossible. Okay, and there's a good heuristic for this, is that if you specialize, right? So if you think about what M is, and if you think about when you restrict to a decomposition group, it's like going to the mod L case, but M is choosing a random subspace. Okay, if you do that, right, then, this is Z mod LZ squared, and there's only one subspace out of the L plus 1 possible subspaces, which is the multiplicative one. So the probability that this restricted representation is what you want is 1 over L plus 1. And so when you have many primes of multiplicative reduction where you're trying to get this to work, it's not going to happen. There's a proof of this in Mochizuki's original Hajar-Kalev paper, and I think it uses Falting's isogeny theorem, or maybe something less fancy. Okay, but that's the idea. Okay, so we can't have that, right? And so what Mochizuki proposes to do is to not take all of not have a global multiplicative subspace, but to do something simpler, right? And what he does is he Frankensteins his way out of this, right? Or what he does is he'll choose a collection of places that lift, right? So we'll choose, what you do is you judiciously choose your lifts in such a way so that the decomposition group of GV bar over V, right? So that works. Okay, so again, I guess the issue here with the notation previously is that those GVs are defined up to conjugation. And so when you conjugate them, you're really moving the top piece around. You're moving the prime above it. You know, you have kind of your cover, and then you're going to be moving those V's around. Okay, so all right, so the idea is you kind of you fake out. His strategy is to fake out this global multiplicative subspace. Okay, and yeah. All right. So okay, so we're back to what is this initial theta data, and okay. Okay, so we're back to what this initial theta data is. Okay, and so now I'm going to produce an explicit tuple just to hammer everything out. Now, I haven't said all the hypotheses, but hopefully this is an indication that you can do this and you can produce initial theta data. Okay, so one of the conditions is that you need your arithmetic curve to be not arithmetic as a Riemann surface. Okay, and so this means you don't want it to be hyperbolic two-space modulo an arithmetic subgroup. Okay, so there's a bunch of different conditions for arithmeticity. So one is that it is commensurable with SL2Z inside SL2R or PSL2Z, I guess. One is that that it is Margulis arithmetic, and then there's another thing called Shimura arithmetic. Okay, this hypothesis is needed for constructions of terminal objects and categories. So this is used in one of Mochizuki's reconstruction theorems. Okay, so okay, it's not arithmetic, but this one is super close, and it scared the crap out of me. Okay, is if you think about it, right? It's this particular elliptic curve is x naught of 11, so which is it's its own modular curve, right? And so, but the deal is, why does it not work? Well, okay, so there's kind of one reason that it doesn't work is because we have these 2 points at infinity, and so this isn't a compact thing if you were to quotient it. You need it to be full list of ones that are not allowed to satisfy this condition. So it's generically not the case, right? The motto originally is that you need this thing not to be a Shimura curve, okay? But I guess it's a Shimura curve in some generalized sense because in principle you could have some non-congruent subgroups, so depends on your definition of Shimura curve. Okay, so what are the field conditions? So one of the things that you need is you need 30 torsion in the square root of -1 to be in your field. All right. All right. So okay. So in principle, some of the invariants for these type of fields can be computed, and the expert on this are Harris Daniels and Alvaro Lozano Robledo, yeah, and so so to construct this auxiliary field K that we've been talking about, which appears in a lot of the constructions, is to do this you just adjoin the 13 torsion. So I kind of spoiled it a little bit, but the auxiliary prime here L is going to be 13. Okay. 7 also works. Actually, if you look for a single conductor and if you look at elliptic curves with one bad place, and you go up to prime, you go up to conductors like 10,000 over Q in the LMFDB, about I think you had like 10 or so. There's tons of them, right? Or maybe I went to 10,000. Not 10,000, not up to conductor 10,000. I think I went up to 10,000 entries. About 7 of them. Oh, I don't know what I'm going to say here. So, either 10,000 entries or 10,000 up to conductor 10,000. I think about 7 of them, the first L is equal to 7 didn't work, right? So L is equal to 7 kind of works generically. Okay, so another thing that we needed was a non-empty collection of bad places. Here's a bad place, and here's the tape parameter at the bad place for this particular thing. And so notice it has valuation 5. Okay, and then you need a lift of places. And actually, any lift works here because the lifts of the places in the global multiplicative subspace need to have some compatibility, right? And but in our situation, the compatibility is kind of trivial because there's only one place. Okay, so all right. So again, now I'm going to talk about the prime L, and I wrote down the congruence conditions here. So okay, and right. So in this situation, so I said L is equal to 7 or L is equal to 13 works. I've been talking about L is equal to 13. So we have S is equal to 1, and then we have the degree of the field, and we have the order of the valuation at that prime. Okay, and so you can compute the order of the group, or at least get a set of its factors by knowing that F comes inside the so it's got the I thing, and then the rest of it comes from torsion points, which are a subgroup of these groups here. Okay, so and so you do it for say 2, 3, 5, and that's it, right? And so you check that the divisibility to unhinged, and those are the conditions in the box. Also, you need that okay, so you don't need rho L to be surjective. You need the image to contain SL2 FL, but surjectivity can be checked. I think even the L-adic representation can be checked in Sage, and I think generically that's the case. Okay, so all right. So now there's two pieces. There's this generator. There's a certain generator of torsion up to an involution, and then there's this global multiplicative subspace. Okay, and to produce the global multiplicative subspace, well, we'll just produce the root of unity, right, by recognizing it as a torsion point in EQ bar. There are issues with things like you don't have pietic LLL, so but we know that it exists. Okay. So why do you not have pietic LLL? Because the pietic numbers are dense inside Q, right? So yeah, you don't get those lattice basis reduction algorithms. Okay, so yeah, and so here's a way to produce these groups. Okay, all right. Another thing I guess you can view about this M underline, right, is it's really the pair of E and the elliptic curve is a pair of the modular curve x0 11, right? So yeah, so when you have yeah, okay. Also things like the Fricka involution come into play, but it's never explicitly mentioned in IUT in the papers. But there's I think there's some more standard approaches to writing some of these things down. Okay, so we've talked about the initial theta data, and I gave you an example. Okay, and then the details of the example can be found in the manuscript. But now I want to talk a little bit about what Q and theta pilot divisors are. Okay, and okay, so I'm building towards the Stix-Schulze thing. Okay, so there's these two divisors, Arakelov divisors. Okay, and these are two Arakelov degrees, but they're normalized. Okay, the right hand side is the messed up theta divisor. The left hand side again encodes the negative of the minimal discriminant. And in the end computation, you compute this thing, and another minimal discriminant pops up, and then you relate the two. Okay, so this is what this guy is, And so you actually go over the set of bad places, but for now we'll just assume it's everything for simplicity. Okay, and then this thing is this like kind of, okay, they're actually both, yeah, this one's more of a fake RRKLF divisor, I guess. I mean, they're both kind of RRKLF divisors. But we're going to fake them out. This is certainly in fake regions. In what do I mean by fake? I mean that you're not going to use all the places, but you're going to use a subset of places, and then you're going to do some sort of crazy normalization, right? So that that this works. And the normalization changes throughout the papers, which was kind of a pain. And this is something that we thought was a good service to do, was to kind of clean up some of the notation so that people can so some of the conventions and notation so that it's consistent. Okay, so there's kind of two normalizations for these volumes that you can use, and they're different, and then you have to write down the conversion between them, and keeping track of the normalization all throughout the papers is a little bit of a pain. Okay, so again, so we talked about this. I've been saying what this theta pilot is a tuple of things. So, and here's the tuple, right? So this is the tuple, and S is the set of bad places here. Okay, and so the 2 degrees of the Q pilot and the theta pilot object are related in a very trivial way, right? And so by definition, the degree of this tuple is the expectation of the degrees of this one. And so if you compute this out, you just get like a sum of j squareds, but then you divide by L minus 1 over 2, because you're taking a uniform average of these things. So one of the things you'll see is that it's all in terms of kind of random. One way to think about it is you're taking a lot of expectations. Okay, so anyway, this degree and this degree are related in a very trivial way, and this is the not messed up region, the not messed up version of the pilot object. But the point about this going through the theta construction is that it allegedly allows you to mess it up and reconstruct it up to automorphism. Okay, so all right, so maybe you guys have seen this, right? So this is about the discussions on IUT, and so one of the things that everyone is keeping track of is so actually in the papers, right? So right now I've been working with real numbers, right? And so, but what is actually happening is that there's these global Frobinioids that have which Mochizuki calls, which contain unit group and value group portions, which means there's kind of like 2 monoids associated with them, and then an abstract version of our RRKLF divisors. So what's a Frobinioid, first of all? A Frobinioid is really an abstraction of the notion of divisors, right? In line bundles and so divisors and rational divisors. So it gives you everything you need to make a Picard group. Okay, and so okay, so after you realify, so one thing that you can check is that after you tensor up the RRKLF divisor class group up to the reals, it's isomorphic to the reals. Okay, so what else do I want to say about this? Okay. So one of the things that they were trying to, so one of the things they proposed to do, which actually isn't quite in the papers, is to keep track of the identifications that are made in the paper, right? And they say that the degree of the Q pilot lives in here. Again, this is again for abstract versions. So this is the degree of the theta pilot lives here, and so this is like the Frobinioid theoretic degree. And these things are objects of Frobinioids, and so they make this identification, and so in this abstract case, you can always map it to the real numbers under the real numbers that I just gave you previously, right? Similarly, for the measures of spaces, there's a way to normalize the measures on So and so that there's no there's you could do that if you wanted to, all right? And one of the things that that Mochizuki says is that you should identify these two things, okay? But what they also said is that they wanted to fix the kind of the normalization, and so when you fix the normalization, if you want to fix this to be the number that we wrote before, and you want to fix this to be the number that you wrote before, and you want them to match each other, well, that's asking for two things to be equal and not equal at the same time, right? So the idea is that maybe I should have written the degree here and the degree there, but the point is the statement that they were making is that he was saying that you want something to be equal and not equal at the same time if you fix the normalizations of your degrees in these global realified Frobenioids. If you fix them in the way that is kind of like the obvious way you would want to do it, right? Meaning that this thing should have its degree and this thing should have its degree, according to the computation on the previous page, meaning that they differ by this like L times L minus 1 divided by 12 thing. Okay? So, but the thing is that we're not supposed to do this, okay? And so, okay, so one of the reasons why I know not to do this is because, okay, so this is not a disproof, right? Because this, you're not allowed to do this loop here on this side, okay? All right, so this is one thing that they did, but they weren't the first people to do this, right? And so, you can see that there's another similar diagram here in an older manuscript, right? And this was retracted, right? So and it was never put on the web or anything like this. It was just something that where someone was trying to figure something out, and and so also, I have made the mistake myself as well. And it makes sense to me that you're not allowed to do this. And I think it would be really silly if the whole thing boiled down to something like this. It doesn't, right? Okay. So, all right. So how did Mochizuki respond? So I think you could say that his response was a little hostile. So he compared them to unfavorably to undergraduates twice, right? And I need to make sure that I have Northcott's theorem correct, or else I'm going to get hammered. I'm spelling Northcott right. Okay. Okay, so this is Northcott's theorem. And so I think at this point, people stopped reading, right? But if you kind of follow it closely enough, you'll see that it says comment 9, but it should be comment 12, addresses this issue that I was talking about where there's this identification between the two things, right? And so, so they made this identification that's not allowed, right? There are other things that that I've discussed with Peter online, and and so those are, I think, are on Peter White's blog. I would read the comments because I think the document he put is abridged. Okay. All right. So now I'm going to give a little bit of a description of the measure spaces. So I guess I don't have so much time right now. Okay. So let's try and describe what these measure spaces are. Okay. So again, here are some of the normalization issues. So you can see that from IUT3 to IUT4, the normalization changes. One of the reasons is because in this monoanalytic setting, which means reconstructed from absolute Galois groups of local fields, for the most part. I think Mochizuki reserves the term monoanalytic for other things sometimes, so it's not always consistent. So you cannot reconstruct a field from from the absolute Galois group of a number field, which means you can't reconstruct the ring of integers, which means you need some other discrete subspace in order to normalize your measure with. And the thing that he uses there are these things called log shells. Okay, so yeah, so this is one normalization in IET4. This is another normalization in IET2. They're different. And so, okay. But, you know, one of the issues is to keep track of these things. Okay? Keeping track of bookkeeping is an issue, especially given, you know, how that RAM issue with, you know, that your brain can only hold so many definitions at once, right? Okay, so so didn't I already do this? But p theta really isn't a fake Arkelov divisor. Okay, so now I'm going to give a description of the measure spaces and hopefully build towards the computation. All right. Okay, so one of the things we wanted to do is provide a service because, well, in this slide's maybe not the most relevant. I guess in here you can see some of the measure spaces that are involved on the right-hand side in IUT. And so every time they're instantiated in the paper, they come with an interpretation. So there's 4 flavors of these things. There's what Mochizuki calls, well, there's an a holomorphic and monoanalytic ones, and then there's the étale and holomorphic. Sorry, Frobenius-like and étale-like, and holomorphic and monoanalytic. And so so in order to kind of simplify the presentation for people who don't want to get involved in all of this, we've developed like a standalone terminology that can be used just for computations. Okay. So again, recall that these are the 2 basic objects here. This is the inequality, right? And there's kind of 2 things that come into play. There's the Q-pilot, and then the Q-pilot divisor, and then the theta pilot divisor, but the messed up version of the theta pilot divisor. So the Q-pilot divisor, this is just an ordinary Arkelov divisor. Again, its degree is related to the negative. So its degree is the discriminant. So this side is the negative of the log of the minimal discriminant, the norm of the minimal discriminant of a field, and then I guess divided by 2 pi or 2L divided by the degree of the field extension. Okay, so okay, and then there's this other one which is not a real Arkelov divisor. First because it's a tuple, but also because we have to use that V underline to construct these places. And so I want to describe this region a little bit in the measures for the purposes of kind of indicating what goes into doing these computations. Okay, so this space here, this is the fake Adeles here. And so this thing is a direct sum of places at finite p. So that should be a direct sum over p. Okay, I guess I put it in now. And then in here, you see the fake Adeles at p. All right, so, and then this is tensored up to the j plus 1. Okay, and so now I'm going to describe this other piece, right? And so this is a tensor power of these Adeles. So note that if you just had this direct sum of when it divides p, that would look more like the Adeles, where you take like kind of a restricted product over all the places. Okay, we're not going to worry about the restricted product topology. What we will worry about is so here we're looking. So here we're only looking at a product of places in K that are above P with this section. Okay, and that's kind of why it's fake, the fake Adeles, because we're not using all the places. Okay, and we want to mimic our Arkelov divisors, in kind of our Kalev degree or in Adelic computations with just this restricted number of places. Okay, so one of the main tricks is that we kind of want invariance under base extension for finite fields, or for p-adic fields, and one of the key facts for p-adic vector spaces is that multiplication by p shrinks the region by p to the negative dimension. Okay? So what we're going to do is renormalize all of our degrees, right? So all of our measures, right, our log measures, and we're going to define when we put a bar over like this. So that should be a log mu w. Okay, so Mochizuki's idea is to normalize all the measures here, and in the following way. So measures of p-adic vector spaces by taking logs of them, right? That way, it doesn't really know about its dimension, right? After you multiply by an element, okay? And you can see that if you take the Haar measure for something over the field of moduli at a place, and then you extend, or you take the Haar measure for at an extension above it, then if you multiply by an element A and F0 on the unit disk in both of those, then you're going to get the same result. Okay, so all right. So this is how we're going to kind of mess around with these things. Okay, so we had those three things, and I'm going to look at the bottom one now. And the bottom one decomposes as so. Okay, and we can just maybe denote this thing by LV. All right, so I'm going to describe our measure process now. So so in the formula for these for the log volume of the whole of the multi-radial representation, so this whole of u theta thing, right? We have this measure, okay? And this is what comes up in the computation. So here, if we take products like so, inside these LVs, so these are going to be random measurable sets. So these are just products of subspaces of p-adic vector spaces, okay? And what we do is we think of, we think of a random measure as, so we kind of think of this function, so this is the expectation of the random measure, right? And so we kind of think of a function where we assign this tuple of places, right, to a measure, right? So we have this, or you can think of a tuple of places is given a random set, the AV, and then when we take the expectation of the measures of this random set, then this is how we compute this kind of probability measure. So in particular, the measures in Mochizuki's theory are not measures at all, right? They're random measures. They're expectations of measures of random measurable sets in this following sense. Okay, so what is this thing exactly? So how do we compute this thing? So all we need to do is to give these vector v's a probability. Okay, and to get the vector v's a probability, well, if we're going to view that as an element of a product of probability spaces, and so we just kind of need to give the basic probability. And so for a place in the field of moduli, we define the probability of that place occurring, right, for all the places over P as in the following way. Okay? So this is how we can. So one of okay. So I want to describe a little bit about this bottom piece, since all the computations are local, right? And how these things appear. So you can break down this bottom piece as kind of. So this is the Adeles at a prime, as kind of when you take this big this tensor power, you'll get a big product of fields, right? The lifted completions, right? And the types of things that we're going to be taking measures of are measurable subsets of each of those factors, each of the factors of the summand, okay? And so what you do to do this is, so you'll take the kind of expected value of the measure, the expected value of the measure of each of those sets. This is the way this thing shakes down, okay? And so how do you do this expectation? Well, the key formula is that, so the probability associated to a single element V is this ratio here. So you have this degree, and the sum of the local degrees is equal to the global degree, right? And so if you weight things by this proportion, you'll get, and then okay, this is on a single thing, but then you can do products of them, and then after you have products of them, then you can do, say, direct sums of products of things, and then and then you do each of those uniformly, and then you'll have j plus one of those, and that's how those fit together. Okay, so all right. Okay, so now I want to talk a little bit about the theorem 1.10, which is the derivation of these inequalities. Okay, so okay, so there's these so if you were just going to open up the paper, right, you'll run into some issues, which are some really weird notations. This mixture, like I said, of divisors and volumes, which is not clear exactly how they're converting between them. There's kind of some troll theorems, which is the sum of the sum of m number, the sum of numbers 1 through n. There's kind of conductor different inequalities. There's weird divisor things that are appearing, which seem to be unmotivated. There are so there's some other notation. It's a little bit of a mess in 1, 2, 3, 4, 5, 6, 7, 8, 9 pages, right? And so you kind of to read this, you need to kind of compile all the results and make sure that you understand the definitions from the previous papers, the relevant definitions from the previous papers, which we've tried to compile for as a reference for people. Okay, so now I'm just going to kind of do some rapid fire things about how does what appear where. Okay, so how do conductors appear in the formula? Well, there's okay, so they come through ramification indices. And how do ramification indices appear? Well, those appear through volumes of log shells. So really, there's a complicated theorem, which is proposition 1.8 of IU24, which is 4 pages about. And I mean, it's a little less, right? It's about 2 pages, but or 3 pages. And so and so if you read this, it's a little confusing about how this is applied, but you can replace everything they do with just a systematic application of this Serre-Tate theorem, right? Which tells you that about ramification degrees in the L torsion fields, okay, for an abelian varieties. And it says that ramification comes from one of 2 places. Okay, it comes from, the L that you used, right? So I guess that doesn't really count. Or it comes from the conductor or the discriminant, okay? And the different and the discriminant are related because the norm of the different is the discriminant, Okay, so one thing that you can do once we carry this out is we can actually compute all the constants explicitly. We do, because we're making some simplifications, we get this exponent 24, and I'm not exactly sure how much better you can make this, but here are the numbers with an explicit epsilon. So epsilon is like O of L squared. There are, as you could expect, these bars are probabilistic versions. So this is the expected, the E bar is the expected value of the ramification index, and the different is is something that you get from the expected value of the different exponents. So so the unramified here, so that's the probability that a place above it will be unramified. So if you wanted to, you could just compute the whole thing probabilistically. You'll get something weaker, right? But it's doable, right? So another thing you could do if you wanted to break down the computation is it's possible to break down the computation just in terms of the number field, right? So here we have the degree and the discriminant of that field, the L torsion field plus the, where here if we have something over the field of moduli, you adjoin the 30 L torsion square root of minus 1 and the J invariant. If it's defined over if it comes from the field of moduli, this is what you get. Okay. So one of the more interesting things are the indeterminacies, and so the indeterminacies come from forgetting information, right? So this is this business. So the first indeterminacy comes from IUT1, and it's about losing evaluation points. And the second indeterminacy appears different in different guises, which makes it kind of complicated. It appears both in IUT3 and IUT4, but in IUT3 and IUT2, but they appear in different ways. One is always in terms of Fabinioids, the other one's in terms of this Galois group. Okay, so and so maybe I should say a little bit about that one. Okay, so I'm not going to say anything about that. This is the probabilistic version, and that's it.